Again, welcome. This is GenAI for Health, and we're going to kickstart this session by a keynote talk by Hoifung Poon, who is from Microsoft. He's a general manager for Microsoft Health Futures. He has an amazing record and accomplishments at the interface of GenAI and health. I would say probably one of the best guys we could have found. We are very lucky and happy to have you here. He was also named as the Technology Champion of 2024 at the 6th Annual Healthcare Leadership Awards. So it's a big honor to have you here.
Thanks so much for the kind introduction. Can everyone hear me okay? Awesome. It's really excited to be here. And in the past 1.5 days, I actually were able to get out of my own intellectual bubble and start to learn a lot of different topics, right, from agriculture to hydrology, from chip design to material discovery. So in my talk, I will kind of like switch gear a little bit and kind of return to some of the maybe perhaps slightly more mundane topics, such as how can we cure cancer before we get one, right? So it's so excited to see all the kind of interest in AI. Personally, I started my journey 2 decades ago when doing my PhD in machine learning and NLP. That was when AI was in the last ice age. I literally have friends who were in the job market and they have to make a disclaimer that they are not an AI person, right? So it's a very, very different time. And I joined Microsoft Research 14 years ago and started working on this precision medicine. I was actually, at the time, I was really inspired by this 10-year anniversary of Human Genome Project. I was also extremely lucky because I was blessed by ignorance. I didn't know how hard biomed and health is. And by the time I realized it, it's already too late, right? So really here, I'm just try to share some of my own learning over the years with lots of amazing mentor collaborators and teams. So I want to start the talk with kind of like one observation, right? So throughout history, if we think about it, technology really has proven to be the most powerful democratization forces. One example is that every one of us here, right, have much better healthcare than any king and queen in the history, right? So this really start to obviously back the natural question that can we empower everyone in the globe to have the same kind of high-quality healthcare as the most resourced person, right, such as Bill Gates and Steve Jobs, right? And in fact, today's healthcare actually still have a giant growth space, right? For example, Steve Jobs, despite all the resources he has, still unfortunately succumbed to his cancer. So we might actually want to aim even higher, is to say, can we empower everyone to have better healthcare, right, than actually today's most resourced person? So this talk is essentially one long argument to say that both of these goals are not completely crazy, right? So in fact, with given the Gen AI revolution, arguably we already start knocking at the door, right? Now, it's so good to see the excitement about Gen AI, but I should also emphasize that we are still very, very, very early, right? So some people liken this to the moment when we first figure out that copper wire can conduct electricity, right? So on one hand, we are still searching for the equivalent of the light bulb, right? And in the same time, we need to be careful not to do the equivalent of electrocuting people. So that's a really interesting time, right? And the natural instinct is that we often want to shoehorn Gen AI into the existing workflow, but I want to also highlight that the much greater opportunity actually lies in can we reimagine the entire workflow process, ecosystem, business model, etc. Right? So from a technology point of view, you can think about our entire research program actually boil down to learning the multimodal language of a patient, right? And all those modalities are trying to tell us something about a patient. And if we can figure out what they're saying, we can start to create this so-called virtual patient, right? Essentially a patient digital twin that can be used for prognosis and predictive medicine. So that's exciting, but AI is really no magic, right? So sometimes it may appear magical because we actually apply the right algorithm on the right data. And in biomedicine, actually in the past couple decades, right, there is a really exciting sort of rapid digitization of a lot of the data, right, starting from genomic sequencing to electronic medical records. So there is this sort of long-standing dream about real-world evidence that is now quickly becoming a reality, right? So when you think about it, every day there are literally billions and billions of data points capturing patient journey from diagnosis to treatment to outcome. And if we can crack the code and distill all the insight underneath, right, we essentially have a population scale free lunch, right? Throughout the talk, probably one takeaway you will find is that I'm a firm believer of free lunch, right? And so, of course, real-world evidence is not a new idea, right? People have been milking, like insurance company milking claim data for decades, right? But the big difference is that in the past, a lot of the focus has been limited to the available structured data. And unfortunately, vast majority of the fine-grained patient information actually lie scattered in all those unstructured data, right? From notes to imaging to multi-omics and so forth. And now the Gen AI basically afford us a very, very powerful tool to start to actually understand, interpreting all those kind of unstructured data, right? And so to make our discussion more concrete, let me show you two marquee examples. The first is clinical trial matching. So as many of you know, unfortunately in cancer, standard of care often fail, and then the clinical trial become the last hope. However, even in the US, only a tiny fraction of patients were able to find a matching trial. And ironically, on the flip side, right, many clinical trials fail because they couldn't find patients in time, right? And as you will see very soon, this is actually an example where actually even today's Gen AI, right, can already start ushering in a major transformation. My second example is immunotherapy, right? So as we talked about earlier, actually even today's best healthcare still have a giant growth area. And one example is like think about immunotherapy. That's really the cutting edge of cancer treatment that basically work by mobilizing the immune system to counter, cancer mutation, relapse, and all those kind of good stuff, right? And indeed, there are really spectacular success, such as Keytruda, right, that can work miracle on some of the late-stage patients. And also, many people believe that this is exactly a direction where we eventually will solve cancer, right? Because the immune system has the blessing of natural selection and can really counter a lot of the what make cancer really hard to deal with. However, if you look at even the best kind of immunotherapy today, right, the overall response rate is only 20%. So this is an example where there is actually a giant potential that we can go well beyond even today's what the best doctor can do. When we think about biomedical discovery, obviously top of mind would be the early R&D, right? So these are indeed very foundational, very exciting, but in the grand scheme of things, they're only 10–20% of the cost. The vast majority of those astronomical costs and the time actually lies in a lot of this super mundane later stages, like how do you run a trial, how do you actually conduct post-market surveillance, and so forth. And those happen also to be exactly the sweet spot where real-world evidence can already immediately have an impact. Modular the fact that we have to be able to, figure out those data, right? So then really the trillion-dollar question is that can Gen AI deliver, right? So people joke about like the buzzword basically evolved in the past 3 years, right? From Gen AI to multimodal, and this year, surprise, surprise, is agent, right? When you look under the hood, obviously it's not all pony and rainbows, right? So there is still lots and lots of challenges, and naturally there are also skepticism and so forth. But this really reminds me of this Mara's law, sometimes attributed to Bill Gates, right? That we tend to overestimate short-term progress, right? And that's actually exactly what led to the hype, right? But in the same time, we also tend to underestimate the long-term kind of like transformation, even though those are already happening quietly in the background. So in terms of kind of like Gen AI application, actually the major transformation already happening in the background on the productivity gain side, right? So this is the regime where actually human experts are perfectly capable of doing this stuff, except that it's just so tedious, so time-consuming, so expensive, right? But this is exactly the sweet spot of current Gen AI, especially in the text modality. Now, we are still very far away from automating discovery for creativity gain, but every step along the way can really unleash a giant value creation. So one of the marquee examples for productivity gain is this so-called universal medical abstraction, right? So basically, there is tons of this key information about a cancer patient or any patient, right, that are scattered in all those clinical biomedical texts, right? And prior generation of AI suffered this, what people sometimes jokingly call the death by a thousand cut problem, right? So it's probably not hard to build a particular model to extract a particular attribute from the nodes, right? But when you start to have hundreds, if not thousands of attributes, then you start to get hosts. Now, what's amazing is that the frontier AI today, right, even basically even 2 years ago when GPT-4 first came out, they already have acquired sort of like this kind of amazing capability that can actually start to extract a lot of this kind of attribute out of the box, right, with natural prompt, right? Arguably the minimum thing you have to specify is like what are you trying to extract, right? And those frontier AI are smart enough to be able to actually do that, right? And oftentimes match or even surpass previously sort of like state-of-the-art, like task-specific, attribute-specific models. And also, this is not just, we are not just go easy on Gen AI, right? You can actually put them on some of the really hardest kind of attributes, such as clinical staging, right? AJCC have a 600-page book, right, that basically specify, based on all this condition, right, like whether this staging should be 3A, 2Bs, and so forth. What's really amazing is that you can actually literally ask GPT-4 to read the freaking menu, right? To basically put the instruction into the prompt, and then amazingly, they basically can follow those instructions. So what this implies is that actually already a lot of profound kind of like transformation can already start happening, right? For example, every year 20 million new cancer patients in the globe. Traditionally, right, you hire these poor abstractors or registrar, right? They have to parse through hundreds of nodes, and each cancer patient can take them hours, costing hundreds of dollars, right? And with Gen AI-powered universal medical abstraction, it takes seconds and costs a few cents, right? So what's the implication is that remember our first example, clinical trial matching, right? The implication is that actually on the technology, pure technology front, right, we can already empower, basically we can basically scan all those incoming nodes 24/7, right? And we can scan all the trial, right, and all the updates and what have you, and then we can do 24/7 just-in-time clinical trial matching, right? And so this can already have major implication, and we have over the year we have lots of amazing collaborators in the clinical side, right? In particular, with Providence, a very large health system in the West Coast. Actually, we have shown that this actually can start working end to end, including in some of the high-profile trials that, as reported by New York Times here. And I also want to highlight that clinical trial matching in the grand scheme of things is very important, but it's only a kind of appetizer, right? So what the capability can enable you to do is to reimagine the entire clinical trial operation, right? A single cancer trial right now can cost you $100 million, right? And a lot of saving and speed up can potentially already at our fingertip, right? For example, one really major implication is also health equity. So even in the US, 85% of cancer patients are treated in these community rural hospitals, right? And they often are completely ignored. They are like the dark matters for clinical trials, right? Because they simply don't have the resource to hire those trial coordinators to be able to match them to the trial. But with this technology, we can already arguably instantly kind of like democratizing all this access, right? And actually enable all those patients to be able to have the trial. And then for the sponsor side, right? For the PI side, they can easily figure out where are the patients, right? Today it's purely guessing game, but you can actually give them a tool to say, give me any trial criteria, right? I can immediately tell you where are those patients, how many of them historically, what are the trends, and so forth. So this is very exciting. But this is only the tips of the iceberg, right? So when you think about text, right, it's obviously an 80-20 modality for patients' information, but they are really sort of like just imperfect human translations. So over the years, I make a lot of friends in clinical side, right? They tell me all kinds of jokes, right? So radiologists will tell me that sometimes they don't agree with themselves 2 weeks ago, right? And pathology told me that if they turn the pathology slide 90 degrees, sometimes they see different things. Right? And that's obviously very natural, right? Our visual cortex are evolving in the jungle, evading tigers, right? They are not doing MRI back in hunter-gatherer days, right? So the question then is like, can we actually be able to go back to the raw signal, right? So all those CT, MRI, omics, of you like, right? To try to figure out, they are trying to tell us something, but today we are just not doing a very good job in translation, right? Can we do a much better job in translation? I also want to emphasize that individual modality is great, but they are also inherently limited, right? So only by kind of like synthesizing all of them together can we recapitulate sort of a really holistic kind of like patient representation. So I'm a machine learning person by training, so this is my kind of nerdy way to think about what is precision health, right? So I basically think about it as we are trying to learn a function, and then the input is this multimodal information about the patient. And then what do we care about? Essentially are two things, right? One is like, can we predict the disease progression, right? The prognosis. The other thing is, can we predict the counterfactual treatment response? If we can do those two things accurately, then we are really golden, right? Now, obviously, this is not so easy, right? So the patient information is not a snapshot, but actually a longitudinal time series. And most frustratingly is that most of the information you want to know actually is missing, right? And then the observable information often have noise, have biases, and so forth. But this is exactly why Gen AI can be so promising for precision health, because the Gen part, right, is basically referred to this mathematical concept of generative model over the joint distribution of all these variables, right? So it seems like we're trying to do a much more work, but actually end up that we are making our life much easier. And so by basically modeling all this joint distribution, what we end up with is that a really powerful and also principled way to basically say, number one, let's really compress all those observed information, right, into this compact representation of patient embedding, right? And number two, we can invoke the standard probability inference. Conditioning on all those observed variables, we can predict those missing stuff, right? And also, when you think about it, right, the longitudinal medical event prediction, that's basically a special case. So this basically motivates us of a research agenda to say, can we portray a very powerful biomedical frontier model from all those real-world data, right? And then the Gen AI disruption means that now for the first time ever, we can start to imagine building this really high fidelity representation that can almost start to serving as a patient digital twin. Now, given such a digital twin, right, so then at the inference time, we can start to do population, sort of patient-like-me reasoning at the population scale. When you have a cancer patient, right, and if there is a resource, the first thing you would do is to try to look for a second opinion. Now, if we have this kind of patient-like-me reasoning, you can snap your finger and you can get a million second opinion right there, right? You can basically look at all those most similar patients. You can say, hey, what treatment have been applied to them, what kind of outcome have been observed, right? And then you can immediately improve the patient care, right? You can also start to compare all those exceptional responder versus the non-responder, and then you can start to poking at why those 80% of people don't respond to Keytruda, right? So there is a discussion about this, a concept about emergent capability. So basically it means that if you have high enough capacity in your model, right, and you feed it high enough free lunch, right? So let's say the whole public web, right? Then the model will start to have this phase transition in terms of capability, suddenly become really, really good at doing a lot of stuff, right? So now we can really start to imagine what if we were able to start to feeding, let's say 8 billion, right, multimodal longitudinal patient journey, right, to this kind of frontier model, what kind of insight can they unlock, right? So that would be sort of really exciting, and potentially we can now shatter the glass ceiling of today's healthcare common sense and go way beyond to our second goal, right? This is very, very exciting, and I will argue that this is ultimately sort of like the creativity gain, right? Which is like, can we empower human expert, right, to consume, all 30 million papers, 8 billion patient journey? Obviously, we are still far, far away from, getting the moonshot, right? But there are some tiny, tiny baby steps there. One of the really perennial challenges here, right, is that there are so many of all those kind of modality, multimodal complexity, right? And also, not only we have a long tail of this kind of modality, but also we often have very little data here, right? So brute force approach doesn't really work nicely here, right? So over the years, we basically try to figure out, again, as you can see, my font is about free lunch, right? So all we are obsessed about is to figure out what are the recipes to kind of consume those free lunch. And I summarize them to basically 3 big free lunches, right? The first one is basically, I think a lot of the speakers have gave already really nice introduction about, is basically that this idea about like any unannotated data point that you have, you can turn it into a self-supervised training instance by introducing this modality-specific encoder-decoder pair, right? So, and what they do is basically compress the original input and then decompress that to recreate the original input, right? And also for text, there is somebody already spent billions of dollars, so you don't have to do anything, right? Now, this is a very powerful paradigm, but for individual modality, there are also unique challenges, right? So, for example, in precision immunotherapy, the holy grail is that can we learn to master this so-called tumor microenvironment grammar, right? So that basically model how those tumor cell, immune cell interact with each other, and actually the pattern they interact with each other hidden a lot of the secret about whether the patient can respond to the immunotherapy or not, and also can we fundamentally reprogram the so-called cold tumor, right, into the hot, which will respond to the therapy, right? If we can figure out the grammar, we basically are done, right? So this is actually sort of like motivate us to start looking into digital pathology, right? And arguably, we already have a very powerful tool, right? So all of you are probably familiar with Transformer, which is the workhorse of the modern Gen AI. And it basically works by essentially modeling, you have image, right? You have 2 pixels. You basically try to pass messages between the 2 pixels repeatedly, right? It can basically, in this way, it can capture arbitrary complex patterns, right, in the image. However, it has one Achilles heel, right? Because it has to model those pairwise, dependency, then the computation grows quadratically in the input size. Now, unfortunately, digital pathology has among the largest images in the world, right? So a single slide, if you're using standard transformer, right, a single slide will cost you 1 billion times in compute compared to standard web images, right? Like cat and dog is fine, right? Once you go to digital path, like that's a challenge, right? We are really lucky to have amazing collaborators from Providence, for example, in this case, and University of Washington. We basically steal an idea called diluted attention from speech recognition, and then to adapt that to digital pathology. So in the interest of time, I wouldn't go, I would point you to our paper in Nature. We essentially, in this way, we basically developed the first digital pathology foundation model that can truly scale transformer to the whole slide images, right? So since our Nature paper publication, really excited to see actually the download have been already exceeded 1 million times. Even more excitingly is that some researcher in Mount Sinai and Eli Lilly, they basically conducted the first they demonstrate the first real-world, real-time clinical deployment of a fine-tuned gigapath model for precision oncology across multiple continents and institutions, and they recently published this in Nature Medicine, and those are really the sort of the gratifying moment for us. This is great, and also there was exciting progress in like CT, MRI, single cells, and all those good stuff, right? But even assuming that we learn a really good unimodal language, right? Even if we can figure out how to represent individual modality, we still have a second but even bigger challenge, right? So each of those modality, you can think about them as basically telling you something, but in a distinct language. So essentially, we basically have a United Nations problem here, right? So we have lots of languages, right? And they each speak gobbledygook to each other, right? So what we basically need to figure out is that how can we do translation across those modalities, right? So our machine translation friend, what they do is that they basically introduce this resource-rich language, typically English, right? They're using that as a bridge and so-called interlingua to basically bridge across all those languages, right? So you can translate from language A to English and translate from English to language B, right? So this is exactly how commercial MT system, machine translation system, scale to hundreds of languages in the world. So what we are proposing here is that let's steal their playbook, right? And there is a very natural kind of interlingua modality, which is the text, right? We already have very powerful kind of like foundation model for the text modality, right? But also, we also have the second kind of giant free lunch here, right? So for any modality under the sun, right, even the most exciting cutting edge new stuff, typically the study of that modality is conducted in natural language, which means that you will leave paper trail, right? So for example, you have a radiology image, oftentimes you can find a radiology report, you have a pathology slide, you will find a pathology report. Those are imperfect human translation, but still they are kind of like free lunch, right? So as long as the signal outweighs the noise, they can give you sort of like some nutrient, right? So then what we are basically trying to do is to piggyback on those encoder, decoder you already learned in the first stage, right? And then we're just focusing all our attention and compute to train a lightweight adapter layer that essentially serves as a translator, right? So you basically do this for individual modalities. So now you basically modularize your modeling. So now you avoid some of the extreme data sparsity, right? You can also implicitly align everybody to the text semantic space, right? So now they start to talk in a similar kind of like variant of the language. And also another advantage is that the text, all this kind of frontier LLM, right? They already capture entire world's knowledge, right? So you throw in a EGFR or a gene, right? Or maybe a diabetes or something. They don't see it just as a string, right? They basically have all the knowledge about those concepts behind the scene. So now by actually grounding the modality to the text semantic space, you also allow implicit backprog of the knowledge infusion back to the interpreting all those individual modalities, right? So in the interest of time, I would not go into technical detail. You can check out some of our early work on LLaMAT that start to sketch a general recipe here, right? More recently, we basically following this approach, using the natural language as a unifier to essentially develop this biomap parse model that basically bridge across 9 imaging modality, 64 object types, right? This basically enable you to essentially, you can talk to the image, right? You can conduct elaborate, holistic image analysis by essentially just talk, right? So very excited to see just before the workshop, I checked the monthly download count. It become a little bit obsessive, right? But I saw it just surpassed 2 million times. Really try to wonder where are those people, right? So, but very, very exciting. So in the same issue of our paper, Nature Method also published an external review that says some nice word about our paper, so really heartening to see that. So far, it's all good, but we still have one more giant, arguably the largest free lunch out there, which is the patient journey themselves, right? So many of you are probably familiar with GPT-4, right? It basically seems to be doing this arguably brain dead way to say, let's predict next token, next token, next token, right? It seems very brain dead, but if you apply that to trillions of tokens, suddenly some magic happens, right? So we are basically proposing that we can actually do the same thing on the patient journey by essentially forcing the model to learn by predicting the next medical event, and so forth, right? In the interest of time, I will not go into too much detail. I will point you to some preliminary paper that we put out. So we try to conduct a first scaling law study of it. Hopefully, in a couple of weeks, there is an even much larger study that with a partner that we can talk more about publicly. All these are really exciting, which also lead us to start to think even bigger and aim higher, right? To say, we don't have to just embed patients, right? But we can actually embed the trial, we can embed the drugs and so forth. And so eventually we can potentially develop this so-called sort of like universal embedding calculus, right? For precision health and biomedical discovery. That's ultimately we can potentially sort of generalize into really sort of like new domains and rare conditions. Now, there are many, many exciting frontiers, which I don't have time to talk about. Obviously, there are multimodal reasoning, right? So reinforcement learning and all those kind of good stuff. There are agent, right, and so forth. And it's not every day you have your CEO talking about your work on main stage, so that's why I can't resist to put the image there. But I want to conclude by actually leaving with provocative notes, right? So with what we have today, we actually have a really powerful tool already at our disposal, which is that if you give me any research protocol, right, I can snap a finger to conjure up this virtual case arm and virtual control arm, right? And this basically gives us a population scale free lunch on hypothesis generation and testing. Now, this is to show that we are not completely crazy, right? So there is already some very promising, even though very preliminary work with our collaborator at Providence. We basically show that for this marquee lung cancer trial, including the original Keytruda trial, right, we can using the real-world data to simulate the published hazard ratio. So I want to add a disclaimer. I'm not saying randomized control trial is going away anytime soon. But what we've started to feel more and more is that we can harness those real-world data to make those trials to be much more efficient, much less costly, much faster, right? So I want to highlight my team who really do all the works, and also our wonderful collaborator without whom we can't do any of this. Thanks so much.
Wonderful talk, and what a great way to start the panel. While, Anant, you're setting up the panel, maybe in the middle of the questions, I can take them while people are setting up. Yes, and then I'll come to you. Yeah. Okay, you can take it.
You had a slide where you had multiple modal, like in the previous couple of slides back, where you had MRI, CT scan, a graph, bar chart. No, just you have to go forward. I think you skipped too much.
Oh, too much?
Where you had a bar chart, where you had CT scan, MRI, like a bar chart, and then he showed what is the... My question is, which type of diseases require which type of information? No. You had a bar chart with CT scan, MRI, like that stacked up, different one, 10 to the power 3 of CT scan, so that one. So is that irrespective of any disease, or you have to throw all that into that? So the reason I'm asking is, my son was diagnosed with something called CRMO, chronic recurring multifocal osteomyelitis. And then after so many tests, so many this, so many that, then they said it is idiopathic. And then they said, okay, it is autoimmune disease. And then finally said, yeah, you will outgrow. So what is the point in all of that? So many data. So I'm just wondering, what is your thought on which disease require what type of data so that you don't put through patients on hundreds of tests?
Absolutely, absolutely. So, in fact, if you look at the NCCN guideline, right? So, for the cancer guideline, some of the most complicated, like non-small cell lung cancer, right? It's a giant decision graph, right? It basically is a sequential process where it's. I think about, again, I'm a machine learning person, so I think about it's every step you try to maximize your information gain, right? So you're trying to, based on your current sort of like hypothesis, what are the more information gain? I think that could provide probably a principal way that we can start to structure those. And I think you also raised another really important question, which is like, so far, there is a reason why we fixated a lot in cancer. It's partially because a lot of the data are already in the clinical, record system. When you think about autoimmune, when you think about mental health, when you think about neuro, a lot of those stuff, the data is actually outside of the clinical, right? So you don't know yet which, number one, we don't know yet which modality give you the ultimate information. And then number two, exactly like you said, it should be an optimal kind of sequential kind of maximize information gain process. Yeah, absolutely.
So anyone has questions? Because it's true. A couple of things. Could you put the slide with Marty Tenenbaum?
Put
you had the slide with Marty Tenenbaum?
Oh, Marty Tenenbaum. Yeah.
I just want to take a photograph.
Yeah, absolutely. Yeah, he's a great mentor and inspiration. So when I first started this journey, Marty is the one who have been basically talking about how AI can help democratizing cancer cares and all that.
Maybe we can go back 40 years or so. Okay.
Small world.
Small world. Yeah.
Awesome.
And anyway, he's a great guy. So the question I have is that we're talking mostly about treating diseases, but you also mentioned preventing diseases. So that is scientific wellness, for example. Like you have all this data that you are coming into the picture. Now what happens is that if you actually have, let's take, as Leroy Hood puts it, blood as a biomarker, and as you're taking this blood longitudinally across the time, you can detect that this guy is potentially going to get a particular type of cancer and prevent our Alzheimer's or Parkinson's, whatever it is, and prevent it before it is happening. So is that being incorporated into it?
So you might notice in my title, I put precision health. When I started, it was precision medicine, right? But that was like treating the disease, right? But eventually what we want is to, if you look at actually the cancer mortality, it's mostly moved by a lot of the prevention, right? So treatment have made some dent, but prevention is a much bigger bang for the buck. Unfortunately, prevention and early screening also have lots of other challenges because your signal to noise ratio are just so low. And then you also worry about over-diagnostic, over-treatments, and so forth. So, for example, Grail is a company, right, that have a grand vision to say take liquid biopsy from blood and be able to detect cancer very early on. So far, I think we haven't got enough powerful data and model yet. But I think that's absolutely the trend, is to go earlier and earlier and do intervention before actually the patient become really sick. Thanks, everyone.
And I'm handing it over to